doctorate student in the mathematics department here at Baylor, and I focus on dynamical systems and topology.
Hi, I'm Geet. I'm at Baylor. I'm a PhD student in physics, and I work on black holes and quantum gravity.
Nice.
And I'm really sorry my camera is not working.
Okay.
Hi, myself Manjula Raman. I'm a first year graduate student in physics department. I'm working on density functional theory, computational one.
Oh, okay. Oh, I didn't know you're a judge. Sorry. It was in the spreadsheet. But great. Good to have you. So our first presentation will be by Axel from Texas State University. And you may begin whenever you're ready.
Great. Good morning, everyone. The title for my project is an algorithmic comparison of pneumonia locating and severity analysis. The mentor that I worked under is Dr. Ivan Ojeda Ruiz. This project was actually done in the 2021 SHARE program held at Texas State University. Excuse me. All right, now to kind of offer a motivation to the project, I want to first offer a definition on a computerized tomography, or CT, and that is a body scanner that's used to analyze the insides of a patient's body. For the purpose of our project, we're going to be focusing on the lungs of a patient's body. And for the problem here, I want to direct your attention on this demonstration here. So we have our ribs, our spine, our lungs, of course, but I want to focus your attention on this part here, this blue tracing that I did. Inside here, we have pneumonia. And the reason why I wanted to focus on that is because when it comes to being diagnosed with COVID-19, your lungs will be contained with pneumonia. But when it comes to determining really whether you need to be placed into an intensive care unit, is really placed on radiologists, trying to manually trace over that pneumonia. Now, the problem with that is that of course can take time when it comes to being very, very, very accurate, but also lead to human error. So for us, we were actually interested on trying to improve that using two methods here. In this case, the normalized cut and k-means. So let's start off with the normalized cut. But to start, I want to first offer some terminology just in case. So here we have a graph, and a graph is a collection of points called nodes or vertices that are connected by lines called edges. Here we have our weights denoted as W, but in terms of the math behind it, we have the following here. The cut between A and B, a sock of A and B, or association between A and B, and the association between B and B, excuse me. Note that A, B, and B are graphs, but by our definition of the normalized cut, if A and B are subgraphs created from removing the edges of graph B, then end cut is defined as the following between A and B. Now, this of course is a lot of math, so I want to offer a demonstration behind everything. So here, the blue line here we have is our cut, but for us, I want you all to focus on this half here as A, and this subgraph here as B. All right. So here, the cut between A and B is going to be equal to the sum of all weights between A and B. So here we have 2 plus 1 plus 2 plus 1 plus 2. That right there is equal to 8. The sock between A and B is technically defined as the sum of all weights that are in the cut A and B, plus any other weight edges that are inside A or B. So in this case, for A, that's 3. So 8 plus 3 will be 11. Same concept for a sock between B and B. That'll be the cut between A and B plus all the other weight edges that are inside the subgraph B. So 4 plus 4 plus 5 plus the cut between A and B, 21. So with all that in mind, we can see that the normalized cut between A and B is roughly about 1.1082. Now, by Shia and Malik, through a proof on optimal partitioning, they showed that the following end cut definition, that's all written out in graph theory, can actually be rewritten as the following minimization problem in terms of linear algebra. Now, the reason why we do that is because for us, we want to efficiently get everything done in a timely manner. So we decided to focus on implementing all of this in MATLAB, in this case, all this here. Now, when it comes to segmentations, we try to differentiate which pixels that we're looking at are pneumonia and which are not. Now, when it comes to end cut, you can obviously see that right here. We're doing with a lot of slicing and dicing. But when it comes to k-means, we're talking a different story. In this case, rather than slicing and dicing, we're going to look at the frame of a CT scan and break it down into separate clusters from darkest to lightest. In the demonstration here, we have 3 clusters. And in here, you see that we have C1, C2, and C3. Those represent the centers or means of the respective clusters. And notice that for each iteration, we're slowly seeing that each center is moving towards its respective cluster, but it's mainly trying to reach towards the center or mean of that cluster. Now, the amount can vary, and that's actually based on what the user enters in terms of K and sedane K means. Now, here's actually the definition of the K means problem. Now, note that it's actually a minimization problem, but through a proof on the K means problem, it can be demonstrated that the following minimization problem can actually be rewritten as a minimization problem. Now, here we have some results on our performance on each of these methods, but just to clarify, here are our original results. Here is the ground truth, which for us is actually technically the work that was performed by a radiologist. In this case, what should be at least expected. And here we actually have the results of our methods in the respective order that we presented them in. So here we have NCUT and here we have K-means. Now, of course, we can see that right off the bat, NCUT does perform a lot more better than K-means, but I will say that when it comes to the research that we've been doing with NCUT, my research mentor's experience with NCUT has actually been broad compared to K-means, which was actually a method that we only looked at just this summer. Now, of course, we can see that while, again, NCUT does perform better than K-means, we wanted to kind of offer more of a deeper look in understanding how these methods actually performed. So to really understand how each of these methods performed when comparing the ground truth, we wanted to look at 4 things: true positive, false positive, true negative, false negative. In that case, we're trying to see how well our results actually compared to, in this case, the ground truth, or in this case, the radiologist's work. Now, to offer a little bit more of a numbers perspective on the quality of these segmentations, we wanted to look at 2 things: accuracy and dice. Accuracy is, of course, how well did our segmentation perform. Dice is a little bit of a different story in that when we were looking at our articles that we've mentioned in this presentation, dice wasn't explicitly defined. And for us, we actually had to modify the formula that was actually given in one article to where we can offer a little bit more of a correct meaning behind it. And based on our understanding, dice is actually almost used to represent how inaccurate was our algorithm. And that's actually based on how we have 2 times CP in the numerator and 2 times CP in the denominator, with false positive and false negative being added in the denominator. Now, here we actually have our results here. Note that for everything else, with the exception of COVID-002 and COVID-003, NCUT does perform better overall when it comes to both accuracy and dice, with the exception, of course, COVID-002 and COVID-003, showing K-means actually outperforming NCUT, but just by just a bit. But excuse me, even then, it's still clear that our work on K-means can still be improved. But regardless, we can see that in the end, NCUT does perform better when it comes to accuracy, but we do see that for dice, our results did have a little bit of a lower result than we were expecting. So we are trying to see if that can be improved. But regardless, our future work is actually on trying to implement constraints to these methods. So far now, we have actually implemented constraints to NCUT. Right now, our focus is on trying to find out how we can actually implement constraints to K-means and trying to see whether these constraints can actually improve the performance of our segmentation. But with that, I'd like to thank the 2021 SURE program for the opportunity to to make this project possible, the Heart of Texas Conference to actually be able to present, and most importantly, Dr. Hedda for the opportunity to really give me the time, effort, and really the passion to actually get this project, out and going. And with that, I will take questions, and thank you very much.
Great, thank you. So first, the judges, if you have any questions, you may ask them.
Hi.
Yeah.
Oh, yeah, we can, since I saw Cordell first, we can have Cordell ask his question.
Okay. Hi. I just want to say very solid presentation. Thank you so much for sharing. My question has to do with the NCUT thing. You might have mentioned this. So NCUT applies to graphs, right? What are you using as your nodes and edges from you take a photo like a CT scan. What do you apply to your nodes and edges?
Yes, so for our nodes, we're actually defining them as the pixels themselves. And
Okay.
as far as I understood when it came to our work, our edges are at least like more of the adjacency. So in this case, the neighborhood, if you will, on how close they are. And of course, that would actually kind of make sense because we don't obviously want to have, one pixel from like the top left corner actually being connected to an edge where it actually has connected to a node in the bottom right corner, So we want to kind of like, offer a little bit more of a closeness almost and try to see, whether segmentation can be performed. But when it comes to, the project itself, we want to kind of, get more of a focus on trying to see, which parts do we see that are pneumonia and which ones are not.
Right.
So it's like I said, 4 pixels are actually defined as nodes themselves. Edges are kind of more of our neighborhood representation of that.
Okay, wonderful.
Great, thank you. Manjula, you can ask your
Yeah.
question.
Hi, nice presentation. If a person is tested positive, COVID positive, how long it will take if you complete all those results and to determine whether the person need to be placed in ICU or not? How long it will take?
That we're not sure yet. We only had time to only do one, but as far as I understand, when it came to analyzing all the frames, at least in terms of count, there were at least like 300, at least more than that. But I can tell you right now that there are some other machines that do segmentation like this. One, I don't know the name off the top of my head, but I know that my research mentor did it mention how when it comes to the performance of one of the technologies that kind of performs a similar approach, it takes almost a day. But for us, we didn't actually take the time to actually manually go through all 300 frames. So that I can't answer, but if you wanted to consider a comparison, a day is what we found to be like at most efficient.
Great, thank you. And finally, Geet, you may ask your question.
Okay, thanks. Solid presentation, Axel. I have a question. So are you aware of any works where people have used machine learning techniques to analyze these data? And if you are aware, like, can you comment anything about which method is better, how efficient they are, and anything on those lines?
Well, in terms of our project, we didn't find anything specific in terms of our focus when it comes to the articles that we've seen hasn't been like specifically focused on COVID-19. We did see one lecture notes on K-means by Amon Shashua. And when it comes to the normalized cut and image segmentation by Sheena Malik, that of course has nothing to do with COVID, but to your question, we didn't really find or look at any articles that were focused on this topic. I don't think we really found anything at all, at least in terms of machine learning focusing on COVID-19. But we wanted to see if we could, maybe to some extent apply, image segmentation to COVID-19. And that was actually at least the idea that I wanted to focus on was more of my interest in this case, like looking at image segmentation and in this case, my research mentor's idea, look at COVID-19. But to answer your question, in terms of articles, I don't think we either looked at them or put them in consideration or found any at all, at least.
Okay. Does your group like intend to like work on something like this, or does your group does not deal with machine learning techniques?
I'm sorry, say it again.
So does your group intend to like work on these machine learning techniques, use these to analyze these data, or your group does not deal with this?
Well, it's just me and my research mentor, but I can tell you right now that I am interested in trying to move this project forward to be my honors thesis for graduating. So I'm at least hoping that we could look at more methods. But right now, our project is actually, this project is actually a little bit on pause right now. We were actually focusing on another project studying COVID-19 transmission in Texas. But right now, I'm at least hoping that when it comes to some of the machine learning methods, I'm hoping to at least like look at more, at least. Right now, we're just, we only looked at 2 methods, being that we were under a time constraint. Of course, this was like in the summer. So right now, I feel like more can technically be done. In this case, like you said, looking at more machine learning methods. But right now, this is just the only two I looked at so far.
Great, thank you.
Great, thank you for your presentation. Anushka, are you ready to present now?
Yeah, I'm ready. And also for the purposes of running this smoothly, I'll leave my camera off.
Okay, that would be okay. Okay, so yeah, Anushka from UNT will be presenting now.
Yeah, my name is Anushka Holdenkar. I study.
Yeah, okay, great. Yeah, we can see your presentation.
Okay, cool, thank you. My name is Anushka Holdenkar. I study biophysics, specifically looking at the myosin filament in my project. So today I'll be showing results from examining images obtained using photolocalization of rabbit skeletal muscle. I'll be talking about the components of a sarcomere, what photolocalization microscopy is, and what quantum dots are. I'll go into my hypothesis, methodology, and results from the images that were obtained, and also I'll be talking about my results. So just a brief overview over the general components of a sarcomere. Muscle is muscle is a contractile tissue that allows the extremities of animals to move and the organs to function. The basic unit is called a sarcomere. I have a diagram on the slide. The parts of the sarcomere that I'll be focusing on are the I band region, A band region, H zone, and C zone, which isn't depicted in the diagram, but you can find it roughly outside of the H zone, but within the A band region. I'll also be using quantum dots. These are inorganic crystals that have an electrical conductivity when stimulated by UV light, so they emit a wavelength of light. And they help in labeling the thick filament in the rabbit skeletal muscle, and these in turn also show up. These are the, once they emit the light, this is what shows up on the microscopic image. So going into a little bit about optical microscopy, the performance of an optical microscopy technique is limited by diffraction, which in turn sets a limit on the resolution of an image. So this is called the diffraction limit. There have been techniques developed to break past this diffraction limit. I've listed a few on there. There are two types. There's classic fluorescence microscopy and probe-based super resolution microscopy techniques that have been used to break past this. The one I will be using revolves around single point localization microscopy. So these are a family of super resolution techniques that improve spatial resolution. So how it works is individual fluorophore molecules are fluorescent molecules are localized from images below diffraction limit to create super resolution images. This is a type of stochastic imaging technique that uses fluorescent probes. And so in my study, it helps to more easily localize fluorophores by turning certain ones on and off. So I used this photolocalization technique in comparison to confocal electron and expansion micrographs. I hypothesized that the super resolution photolocalization microscopy technique will have a higher resolution than conventional confocal microscopy, about the same resolution as expansion, but less clarity than the electron micrograph. So before collecting the fluorophore images, I created the photoactivatable probe, which utilized 5 elements. There's polylysine, the quencher, crosslinker, photolinker, and quantum dot, which consists of the quantum dot, a fluorescent molecule, and an MF20 monoclonal antibody. The antibody is used to target the myosin filament. And so this probe allowed the quantum dots to be photoactivatable. So I took images of rabbit skeletal muscle Once these probes were injected into the muscle filament, they were imaged using confocal microscopy. And then the individual fluorophores were localized, their centers of mass were reduced, and drift correction was applied. So after taking those images, I had a fluorophore stack with randomly turned on photoactivatable quantum dots. This stack consisted of roughly like 450 images or slices, as I call it. So what I did was I broke this large stack into varying substacks with varying amount of slices. I had to keep into account the orientation of the myofibril when the images were taken, since it wasn't completely straight. This is important because depending on the density of fluorophores in a certain region of the image, I would make different sizes of substacks. And so with the substacks that I make, I averaged them using the z-project function in image J, and then I selected individual sarcomere images through duplication of a selected area on a z-projected stack. I collected around 100 total sarcomere images from the average substacks, which amounts to roughly a total of like 5,000 to like 8,000 images that I averaged. I applied transformations on each sarcomere image, and then I averaged those 100 images to produce a final sarcomere image. So here's the sarcomere image. On the left you can see the micrograph, and on the right you'll see the intensity graph, which shows the intensity peaks across the micrograph. So some major sorry about that. I think my PowerPoint stopped working.
That's okay. Take your time.
Sorry about that. Is everything good now?
Yeah, we can still see it.
Okay. Did I leave off here? Really sorry
You're on
about
the
that.
last slide, I believe.
Oh,
By
was
10.
it this one?
Yeah.
Okay, cool. So sorry about that. This is the image I obtained from super resolution photolocalization microscopy. On the left side, you can see the micrograph, and on the right side, you can see the intensity chart. This intensity chart depicts the intensity peaks across the micrograph. Some major peaks to note. So I have the A band labeled there. The A band corresponds to the sort of peaks right before the large peaks you see at the ends of the micrograph. Overall, the visible features on the micrograph are the A band, the H zone, which is kind of that region where you see the large peaks, and the C zone, which is the dip in the micrograph, or the darker gray area. One feature that isn't clearly visible is the M line. And I've also noted the peaks of the I band, or the Z line in the I band, as well as the M line. Here are the other images from expansion microscopy and electron microscopy. The arrows I have labeled, the lighter blue arrows are the I band, or the Z line in the I band, and the darker blue arrow is the M line, or that center region of the sarcomere. And so, as you can see, all three micrographs have a similar dip around the C zone area. However, one thing to notice here is that the I band region, or the Z line, is much more intense in comparison to the electron and expansion micrographs. This is because when I was aligning my sarcomere image, I aligned it based on the I band instead of the center region or M-line region of the sarcomere. This could have resulted in it being much more intense on the outer regions as opposed to the center region of the sarcomere. So going into my results, the electron micrograph produced the sharpest sarcomere image, and then the micrograph obtained from super resolution photolocalization microscopy had the next highest resolution in terms of the clarity of the image. Initially, as I had mentioned earlier, the M-line was used to align, the M-line or the center region was used to align the sarcomere images. However, I later used the I-band as it was more difficult to accurately locate the center of the sarcomere for alignment. And then another difficulty that came upon me as I was doing my study was finding individual sarcomere images from the average substacks was difficult because the stack itself had low signal density, and therefore I wasn't able to find a lot of images that had enough fluorophores to show a sarcomere. So in conclusion, super resolution photolocalization microscopy generated a sarcomere image that can be improved by averaging images to increase the number of observed fluorophores. The quality of the image is limited primarily by the number of fluorophores or the signal density and alignment issues. However, the resolution was better than conventional confocal microscopy, and it also confirmed the location of structural details such as the sarcomere A band, the M line, and C zone areas. And then, thank you. Oh, sorry about that. Thank you.
Okay, Joshua, you're on mute.
Oh, sorry about that. Thank you, Anushka, for your presentation. Now, judges, do you have any questions for Anushka? Yes, Cordell?
Hi. Again, thank you for your presentation. I thought that was delightful. So my question is, do you have any like further work, something along those lines? Like, where do you go from here?
So I currently also have another set of myosin filaments that have been labeled in a similar way, using like this technique that I learned from how to average these fluorophores. I'll probably use what I learned from this onto those images as well. We hope to continue this to see results in photolocalization, primarily because it's so a lot of people turn to electron microscopy when imaging fine structural details. However, this isn't as nearly as of an expensive process than electron microscopy, and therefore we're looking for ways to improve this technique so that it can meet the clarity or the resolution of electron microscopy.
That's awesome. Thank you.
Great, thank you. Keith, you may ask your question.
I'm sorry.
Oh, no problem, no problem.
Okay. Okay. So, Anushka, great talk. So I probably have a very basic question. So can you explain us, well, I think the motivation is the motivation for you guys to, like, work on rapid skeletal imaging so that you can transfer that to, like, the human, Do you
Uh,
guys intend to do that? If you guys intend to do that, like, does it help in, I don't know, treating injuries or like, detecting them? I am not an expert in this field, so you have to explain us.
yeah. So, right, I guess the long-term goal is to, I guess, it's an indirect, it's very indirect in helping, like, I guess medicine or hospitals. The main goal of this technique is to understand the interactions between different filaments, and also it can be used um, to figure out interactions between filaments and other other uh, I guess proteins. This technique, I mean, this is one of other experiments in our lab, and uh, this can be help in those experiments to analyze how other proteins, when inserted into a filament, can affect the function of the filament itself. So it doesn't have a direct application to hospital or medicine purposes, but it's used at the very fine level to see the interactions between myosin filaments or other filaments, other muscle filaments. Um, our, I guess also our lab focuses on cardiomyopathy of tissue, of muscle tissue, or yeah, focuses on the muscle tissue of those diagnosed with cardiomyopathy. And so looking at those base structural details through techniques, microscopy techniques such as this, will help in experiments that are being done to help prevent cardiomyopathy or understand cardiomyopathy.
Got it. Thank you.
Great, thank you. Yeah, go ahead.
Hi, I have the same question as like Geet asked, like what is the benefits of this, and like can you explain the process of this? Like once you got the image of skeleton, like how you proceed further?
So I guess as what I already sorry about that. As what I already mentioned, so these images are in the end used to create an image that is higher resolution, but that can that is a clear image where you're able to see the details of the sarcomere, and able to see the details of the sarcomere, and it's eventually supposed to be, I guess, not used as a complete alternative, but used as a method as opposed to electron microscopy, which is a much more expensive process. In the end, this technique will aid in looking at the fine details of a sarcomere filament to understand the interaction between different filaments or filaments with other types of proteins. Through these interactions, we're able to do experiments that can help analyze like how or the interactions of filaments and proteins of tissues or muscle tissues of patients with cardiomyopathy, and so we're able to understand what goes on at the molecular level. In the end, these studies can be used to I guess create drugs that will help benefit or help patients with cardiomyopathy. So in the end, it's mainly about that part.
Okay.
Great, thank you. So,
I have another
yeah.
question.
Yeah, go ahead.
So I know you said that you tried to align the sarcomere via the M band, but you had some difficulty doing that. I guess my question is, do you think if you could align it via M band, that that M band would appear just as bright in your final result as the I think it's the I band appears really bright now. If you aligned it by the M band, it would appear that bright.
Yeah, so so after aligning it with the M band, there was a similar the pattern of brightness towards the region where I aligned it. So the M line was brighter than the I band, which suggests that where you align the images affects which areas of the sarcomere are more brighter or more intense. Yeah, that's one thing I got learned from averaging them. Yeah.
Okay, very cool.
Great.
Thank you.
Thank you for the questions. And Axel, do you have any questions for her?
Not right now, no.
Okay, great. No problem. Okay, so that is it for the presentations. Thank you to all the presenters. You did a wonderful job. And this concludes the Math and Physics division. Anushka, if you're able to, could you exit the screen sharing? Yeah, so we're gonna take a group photo for the HOT Instagram. If you guys would like, you could show your face and yeah. So whenever you're ready, I'll count down to 1 and you can smile or show your school sign. So 3, 2, 1. Great, thank you. So now judges can please stay on the Zoom call so you can review comments and deliberate, and the awards will be announced after the keynote speech today, and feedback will be emailed after the conference is over. So yeah, the next event is the graduate school fair, which is around 12, I believe. So you can now leave the Zoom call and refer to the program and find the link in the school fair. Great, thank you. Okay, yeah, so if you guys would like, you can discuss about the awards and what you thought.
Yeah, I thought both presenters did a solid job. With our first presenter with Axel, really my only complaint is that he spoke way too fast.
Right.
But other than that, I think everything was very well done, and I thought his results and his methodology were really nice. And then with the second presenter, with Anushka, again, kind of my only complaint. One, there's technical difficulties, but I can't like hold her at fault for that. And then 2, I think the slides were a little overcrowded, and it was hard, at least for me, to try and read everything and listen to what she was saying. So I think it would have been easier to follow if it were just more sparsely displayed. But other than that, I think both presentations were very nice.
Yeah, I agree with them. Both talks were great. I think with Axel, that was a very good presentation. I think the only thing is one thing is like definitely he was fast, but I'm also fast in my presentation. So, but but then I think the other thing was I think there's like a flow missing between each of the slides, because I think some slides were abruptly ending, and then the flow. I think that's there's obviously room for improvement for everybody, but I think that's the only thing I could point out. And I think for Anushka, there were technical difficulties, but then I don't know. I would usually try to do a pre-run to test these things. So yeah, so I it's not good to hold them accountable for that, but then still yeah. And I see that there's a lack of motivation initially, and then I don't see the punchline in the end of the talk. And yeah, I mean, I'm definitely not an expert. I'm I'm a physics PhD, so it's not my line of work, but then yeah, but it was great work. I can see how much effort they've put into this to bring everything out. Yeah, but yeah, I'll let Manjula Go ahead.
Hi. It's good initiative like to do all those stuff, but as everyone said, I will go with the first person. He given the future talk also, like what is his future goal and everything he was mentioned in the slides, and it was like I like the way he did, and it was little bit fast and somewhere it's a bit difficult to understand, but overall he did better comparing to Anushka. The overall performance is better, and Anushka, like the motivation is less for her, like somewhere she like just stuck in between due to technical also, and also she's stuck in between like while explaining the concepts and everything also. It's like as Geet said, it's a better initiative if you did like 15 minutes before just to check or either everything is working fine or not. Yeah, that's it.
Great. Thank you for your feedback. Yeah, so if you guys would like, you could join in on the keynote speaker. I'll post the Zoom link in the chat.
Thank you.
And
How
yeah,
can I find the Zoom link to the docs that are coming up next?
yeah,
So,
yeah, I just posted
Yeah.
it in the chat. So if you'd like to save that, it should open at 1. And if you want to attend in person, it will be at the BSB and D110. But otherwise, yeah, you could tune in on the Zoom link.
Okay, got it.
Yeah, 3 people are listed in the presentation, but only 2 of them did, right?
Yeah, so the person from UT Austin, Jonathan Tebow, he withdrew. So yeah, that's why he wasn't here to present.
Okay.
But yeah, it's quite unfortunate. But yeah, so that will be it for today. Thank you for being judges, and you guys are able to go on with your day.
Thank you.
Oh, I have a question.
Oh yeah, go ahead.
So when it comes to submitting the Google form, the questions, like the feedback for Jonathan Tebow, should we just put like NA
Yeah,
on
we couldn't
those?
submit it.
Yeah, you can just say NA or did not show up. Yeah.
You got it.
Okay.
Thank you so much for
Yeah.
moderating this and for
Thank
helping
you.
put this event on.
Thank you guys for judging. Couldn't
of
be done
course.
without you guys.
Okay, thank you.
See you later.
Thank you.